Hello, in this video we're going to start chapter 10, which is about acids and bases. So we've already done a lab where we investigated the acidity or basicity of different solutions, and we saw the pH scale. So we're going to dive a little bit deeper into what acids and bases are. So to start, acids are typically going to have a sour taste. So lemon juice is acidic, and that obviously is very sour if you've ever had lemon before. As we saw in our pH lab, acids are going to turn blue paper or blue litmus paper red. Additionally, acids can react with some metals to produce hydrogen gas. We saw this in our water lab when we reacted magnesium with hydrochloric acid, and we ended up producing magnesium chloride and hydrogen gas. And to balance that equation, we actually reacted magnesium with 2 moles of hydrochloric acid. And finally, acids can dissolve carbonate salts and release CO2. So we saw this in our carbonates lab. We reacted our carbonates with hydrochloric acid. So here I'm just using sodium carbonate. And this gave us water, carbon dioxide, and sodium chloride, a salt. And let's see, I think to balance this equation, we have to put a 2 in front of NaCl and a 2 in front of HCl. So we've already seen a lot of reactions with acids. Now, bases, on the other hand, typically have a bitter taste, and they will turn red litmus paper blue, as we've seen before. And bases are usually slippery to the touch. So this would be something like soap or cleaning products. They're typically basic. Now, there are some very specific definitions for acids and bases. The first one is called the Arrhenius definition. So there was a Swedish chemist named Svante Arrhenius. I think I'm pronouncing that correctly. And he developed the first chemical definitions of acids and bases in the late 1800s. So according to the Arrhenius definitions, an acid is a compound that increases the concentration of hydrogen ions in aqueous solution. So for example, we've used hydrochloric acid a lot this quarter. And if we dissolve hydrochloric acid in water, it splits apart into hydrogen ions and chloride ions. So we're increasing the concentration of hydrogen ions in solution. So hydrochloric acid would be obviously an acid. Now for bases, this is a compound that will increase the concentration of hydroxide ions in aqueous solution. So if we dissolve sodium hydroxide in water, this is also going to split apart into sodium ions and hydroxide ions. So we're increasing the hydroxide ion concentration in solution. So there are a lot of acids and bases, and this is by no means an exhaustive list, but some more common acids, we've seen hydrochloric acid, and if we replace chlorine with the other halogens, we get hydrobromic acid, hydroiodic acid. And then let's see, an acid that contains sulfur is hydrosulfuric acid. But if we go down below, we also have sulfuric acid, H2SO4, and sulfurous acid, H2SO3. Now there's some other acids in here as well. Acetic acid, this is what's in vinegar, and nitric acid and nitrous acid. All right, and then looking at the bases, we have sodium hydroxide, and then we can just replace sodium with different metals and get potassium hydroxide, magnesium hydroxide, etc. Now, as we get further down this list, notice that we have a slightly different base called ammonia, NH3. So this does not have hydroxide in it. And then sodium bicarbonate and calcium carbonate also act as bases. Now we're going to come back to ammonia because ammonia, it doesn't look like it's going to produce hydroxide ions in solution. So how is it still considered a base? But first, let's learn how to name acids. So there are two different types of acids. There's binary acids, which contain hydrogen and one other element. So, for example, this would be HCl. So to name a binary acid, we start with the prefix hydro, and then we put the name of the element, the second element, and end it in ic acid. So HCl becomes hydrochloric acid. Similarly, if we have HBr, which again only has one hydrogen and one other element, this is going to be called hydrobromic acid. So we've got that prefix hydro, and then we've got the first part of bromine, BROM, and then we follow it with ic acid. So binary acids are really easy to name. But acids that are composed of more than two elements, so typically this would be hydrogen and oxygen and some other element, these are named differently. So these will be followed by the suffix ic acid or us acid, and that will depend on the number of oxygen atoms in the formula. And then sometimes we'll put prefixes in front like per and hypo, just to kind of tell the difference between acids. So for example, HNO3 is called nitric acid, and notice we don't have hydro in front, but HNO2, so we're losing an oxygen here, this is called nitrous acid. All right, so I'm not going to test you on naming acids, but I did want to just introduce the idea to you so that you know where these names come from. But let's just practice here a little bit. Let's name the following. So the first one, HF, is a binary acid. And then B is actually a base. So this has OH in it. So see if you can figure out the names for our acid and our base. Okay. So we just learned how to name binary acids. We said we had to start with the prefix hydro. And then we're going to fill in part of the name of the other element. So this is fluorine. So we'll use the beginning of that name. And then we'll end it with ic acid. So it becomes hydrofluoric acid. Now, our base is actually just an ionic compound, and we learned how to name ionic compounds back in chapter 3. So the metal is strontium. And then we have the polyatomic ion hydroxide, and we just keep that the same. We don't have to change it or do anything to it. So this is strontium hydroxide. Also, remember with ionic compounds, we don't have to put a prefix to indicate the number of ions. So for example, we wouldn't name this strontium dihydroxide. We just leave it as strontium hydroxide because we can figure out how many of each ion we have based on the charge. Now earlier I mentioned how ammonia is a base, but it doesn't look like it produces hydroxide ions, just looking at the formula, which is NH3. Because we saw the example of sodium hydroxide, so it's very obvious that it will produce hydroxide ions. So again, notice ammonia does not have hydroxide as part of its formula. So how does ammonia increase the amount of hydroxide ions in aqueous solution? Well, instead of dissociating into hydroxide ions, ammonia molecules will react with water molecules by taking a hydrogen from the water molecule. And this is going to produce an ammonium ion and a hydroxide ion. All right, so notice we're actually going to combine NH3 with one of the hydrogens in water. And this is going to produce the ammonium ion, which is NH4+. Now, what's left over from our water molecule after we take a hydrogen is just the hydroxide ion. So let's draw this in a little more detail. So I'm going to draw the Lewis structure of ammonia and the Lewis structure of water. And again, what ends up happening is NH3 is going to grab a hydrogen from water, and that's going to leave behind the hydroxide ion as a result. So we form NH4 plus and OH minus. So this is how the ammonia base increases the concentration of hydroxide ion in solution by reacting with water. So this is going to bring us to a slightly different definition for acids and bases. So this is called the Bronsted-Lowry definition. In 1923, the Danish scientist Johannes Bronsted and the English scientist Thomas Lowry independently proposed new definitions for acids and bases. So they both got credit for these new definitions. So instead of considering the hydrogen and hydroxide ions, they decided to focus on hydrogen only. So according to this definition, a Bronsted-Lowry acid is a compound that supplies a hydrogen ion in a reaction. And then a Bronsted-Lowry base is a compound that accepts a hydrogen ion in a reaction. So if we look at that same reaction between ammonia and water that we saw earlier, ammonia is going to accept a hydrogen and become NH4+. So Ammonia is a Bronsted-Lowry base because it's going to accept a hydrogen. Water, on the other hand, is supplying the hydrogen or donating the hydrogen. So this is going to be a Bronsted-Lowry acid in this case. Okay. Now, one application of acids and bases here are soluble drugs. So typically, drugs need to be water soluble in order to be their most effective. However, many of the pharmaceutical drugs out there are very complex organic compounds, and they're not soluble or they're only slightly soluble in water. Now, we're made mostly of water, so we need pharmaceutical drugs to dissolve in our system. Fortunately, a lot of these drugs contain nitrogen atoms, and as we just saw with ammonia, which contains nitrogen, nitrogen can accept a hydrogen ion. So we can react a lot of these pharmaceutical drugs with hydrochloric acid, which sounds scary, but what happens is the pharmaceutical drug, which has a nitrogen on it, is going to take a hydrogen or accept a hydrogen from hydrochloric acid, and what's left behind is a chloride ion. Now, once the drug has accepted that hydrogen, nitrogen usually becomes an ion. Usually it becomes positively charged. And that's going to make it much, much easier for water to dissolve that drug. Because remember, water is polar and can dissolve other polar molecules or ionic compounds. So if you ever notice on a bottle for prescriptions or prescription medication, if you notice HCl in the name, kind of like on this one for lidocaine, that doesn't mean that you're taking hydrochloric acid. The acid has actually dissociated into ions. So you're just taking the ionic version of the drug so that it dissolves better in your system. All right, so let's practice now that we know some definitions here for acids and bases. Let's identify water as either a Bronsted-Lowry acid or a Bronsted-Lowry base in the following reactions. So remember, a Bronsted-Lowry acid supplies a hydrogen ion, and then a Bronsted-Lowry base will accept a hydrogen ion. So only looking at water, try to determine if water is supplying a hydrogen to the other reactant or if it's accepting a hydrogen from the other reactant. So pause the video, see if you can identify water as an acid or a base. Okay, so let's look at the first reaction. So looking at water here and looking at the products, it looks like water has become OH minus, because if we look at NO2, it looks like it's gained a hydrogen in the products, right? So water in this case has lost or supplied a hydrogen ion to the other molecule. So water supplied a hydrogen ion to NO2 minus. So would that be a Bronsted-Lowry acid or a Bronsted-Lowry base? An acid. Great. Let's look at the second reaction. And again, we're focusing on water. Now looking at the products, the most similar molecule to water is this hydronium ion, H3O+. So it looks like water gained a hydrogen in this reaction, so that means it accepted a hydrogen. So it accepted H+. Okay, so is that a Bronsted-Lowry acid or a Bronsted-Lowry base? A base. Now, one thing to also notice here, notice in the first reaction, when water lost a hydrogen to become the hydroxide ion, the hydroxide ion is negatively charged. And that's because we lost an H+, right? So H+ and OH- will create water. And water is neutral because we have a plus and a minus joining together. Now in the second reaction, water accepted a hydrogen ion and it became H3O+. So we gained a hydrogen and we gained this positive charge that was on hydrogen. So it became H3O+. So just something to keep in mind as we go ahead. Oh, let's see. My equation is missing here. I'll rewrite it. Yeah, PowerPoint hasn't been working very well today. Now, when acids and bases react with each other, they actually form water and salts. Now, a salt is a general chemical term for any ionic compound that's formed from an acid and a base. So, for example, let's say we react NaOH, which is a base, sodium hydroxide, and hydrochloric acid. So when these two react, we end up forming sodium chloride, which we know is table salt, and water. All right, so notice that the hydroxide ion from our base and the hydrogen from our acid are going to team up and form our water molecule. And then what's left over is sodium and chloride, and they're going to form sodium chloride. Now, water and table salt are neutral. So that's why this reaction is called a neutralization reaction. So acids and bases are going to try to neutralize each other. Now let's talk about how to balance a neutralization reaction. It can be a little bit tricky. So in this reaction, we have sodium hydroxide and sulfuric acid, H2SO4, and they're reacting to produce sodium sulfate, which is the salt, and water. Now, to balance this equation, what I usually do is I balance hydroxide ions and hydrogen ions first. So, for example, in sodium hydroxide, we have one OH minus, one hydroxide ion. But in our acid, sulfuric acid, we have two hydrogens, and I'm going to write them as ions. Now remember, earlier we said that hydroxide and the hydrogen ion can team up to form water. Now, if we want to properly balance this equation, we should have equal amounts of hydroxide ions and hydrogen ions. So it looks like we're missing an OH minus here. So let's multiply NaOH by 2 so that we have two hydroxide ions. And then next, so step 2, we're going to balance the H2O product. So now that we have enough hydroxide ions to match the number of hydrogen ions, how many water molecules can we form? 2. So I'm going to put a 2 in front of H2O since we're making two water molecules. And notice that everything else kind of falls into place. So we now have two sodium ions on the left and two sodium ions on the right. And then we have one sulfate ion on the left and one sulfate ion on the right. So again, this is my little trick for balancing neutralization reactions so that you don't have to do it atom by atom. So first, just balance hydroxide ions and hydrogen ions. And then second, make sure you have the right number of water molecules. Okay. So I think we'll leave it there for this video. In the next video, we'll keep talking about acids and bases.